I'm Clayton Crawford. I'm a product engineer on the 3D Analyst Extension team out of Redlands, and I spend a lot of time working with Lidar and related technology for Esri. And in this session, I'll be talking about our zLAS I/O library and API. And so hopefully I'm going to be providing an overview of what it is, and I'll show a project with code, show how it gets used in ways that it could be useful for your applications, and how you can incorporate support for zLAS in your apps. And I'll talk about where you can find it and licensing and that kind of stuff. How many of you are somewhat familiar with zLAS? I guess if you're in this room, you must know something about it, or you're wondering, you've heard it, but you're kind of clueless. You don't really know, you want to find out. Somewhere in between there. Okay, well, the zLAS lib is a C++ library for reading and writing Esri's zLAS format files. So we can take LAS and convert it into something that's an Esri proprietary format, and it has certain advantages that go along with it, converting formats there. And then we can directly use the zLAS format, and we can also convert back to LAS with it. If you have an application that's already written to use LAS and consume it, it's really easy to incorporate the support for zLAS into that application. And we support all LAS formats up through 1.4, the latest, and all point record formats. We don't have extended support for full waveform information, though. So that's something that's not part of it. 99+% users aren't in need of that, though. And we have support going back to old versions of Visual Studio and higher and whatnot. And we have both 32 and 64-bit versions. And so a little more background information for you. The LAS format is an established standard that ASPRS really owns the, I don't know if copyright's the right term for it, but there's a LAS committee as part of ASPRS, and they kind of define what the standard is and support that. And there's a committee there that writes and owns the spec for it, and Esri has full support for the LAS spec. So if you have LAS data, we can consume LAS directly in ArcGIS applications. But there's kind of an issue with LAS in that it was created originally for data exchange and not for direct use. And the reason here is, why we see this happening is that there's no spatial indexing into the data files. There aren't extra statistics. It's just very plain as a binary format for the sake of trying to keep it small, but it's just very simple, and it's just really meant to be exported from one system and imported to another, where then that system's kind of proprietary formats could optimize the format for that system, and that was the original intent. But because LiDAR data is so voluminous, people really have a hard time to go, the idea of running export-import routines, loading stuff into geodatabases or something that is cost prohibitive with that amount of data. So people would very much like to be able to use LAS directly. And so we've done a lot, as much as we can to try to support that. We do create what we call sidecar files for LAS files that contain spatial index information, so that we can kind of with spatial queries go and find the points in the files based on a spatial query to kind of not have to scan through the whole file to find the points that fall within one small area of interest. We can find exactly what point records we need. And also some extra statistical information we keep in those sidecar files, so we know, for example, what class codes are present in the LAS files. I mean, the LAS spec doesn't even include that in the as part of the spec. You don't know what class codes exist in a file without scanning through the whole thing first to find out. Is the data even classified? You have to read through the file to find out if they're all class 0 or whether there's ground or anything else. And so with the sidecar file, we kind of keep that extra information, and it makes those files more directly usable. But they're still very large. It's not uncommon to have many gigabytes and upwards of terabytes of information stored in large Lidar projects. And so if there was some way of reducing the volume of information and having it still be useful, and say reducing the I/O bandwidth requirements, having some other format could be beneficial there. And so we came up with zLAS as a means of handling that. So we'll compress the LAS format files and have built-in indexing and statistics there, and without loss of any information. We can reorder the point records in the LAS files so that they're spatially coherent. Points that are close to one another in XY space are close to one another inside the file. That's for I/O efficiency. That sorting is an option. It does actually kind of, if you were to decompress back to LAS, the file will be a little different because you changed the point record order. But the actual information content has not been harmed in any way. There's not a loss of information using that sorting option. And so anyway, we can bring files down, I would say on average, a zLAS file is like 15 to 20% the size of the original LAS file from which it was created from. So there's significant savings there. And since we know we're dealing with a specific format, we can optimize that compression. That's how we can get such a nice compression ratio. Whereas if you used a more generic compressor like WinZip, zip files, you get the zip files are 40 to 50% size of the original LAS. So we can take it, a degree farther, in terms of compression when we're working with a specific file format. And we do have a utility app that's available online for converting between LAS and zLAS, compressing and decompressing. That's something you can download from Esri, and it's free. There's no license restrictions on using that utility, shipping it with other software, including it there. There's no restrictions on that. So with our zLAS IO lib, we have a number of constructs that we present for handling the kind of operations here. The primary objects involved is a zLAS reader and a writer to create zLAS files, and then there's a filter object that's used for controlling queries, like if you have you want files of a certain return or points of a certain return or class code. Then you can set these filter properties, and then when you're doing a query on a zLAS file, you can just get back the points of interest using that filter. And then there's what I have labeled as interfaces. It's kind of like COM-like, but it's not COM at all. It's just for the sake of kind of convenience and ease of use in the programming for those. So reader and writers these objects have different methods on them implemented through these so-called interfaces. And then there's the structs and enums here as kind of utilities for decoding and using the information in the files. So I'll talk first about the reader object that we have. And to make it as easy as possible to support zLAS in your applications, we want to present zLAS as LAS. So when you're reading a zLAS file in your code, if you're looking at the header or you're looking at specific point records, we'll decompress the zLAS into memory buffers in LAS format. So you already have code to read a LAS format data. Basically, we hand you LAS format data in memory when you're making calls to this. So that makes it simple. If you're starting from scratch, you could also use structs and arrays to access the information. It's for the sake of convenience. So basically you have two different kind of approaches for reading the LAS information from the zLAS files. So you can take your pick, whatever makes more sense to you. And as I mentioned, there's a filter object. This supports area of interest that you can set for pulling out points of sub-areas. And also you can set certain returns, class codes, and class flags. Those are things like model key points, synthetic points, withheld points, and overlap points. That was a flag that was added in 1.4, I believe. And so you can query specifically based on those attributes. And we create like enumerators that facilitate looping through the points that are returned by your query. We also have something that's we refer to as a point data mask. And this is interesting. Like if you're only interested in the point geometry, but not the point attributes, you can set the data mask to just say, I'm just interested in the X, Y, and Z information. And then we don't need to go through the effort of decompressing the attributes that you're not interested in. So that's one of the nice properties of zLAS, is that we have separately compressed attribute channels. So returns, class codes, scan angle rank, intensity, those are all considered different attributes in their own separate channels. And so instead of decompressing all those attributes per point record, we can selectively just decompress what's needed. It improves efficiency in that regard. And then also I mentioned that standard LAS is lacking some information, like what class codes are in the file, for example, and we have that extra information that's burned into the zLAS format, and it's just kept in zLAS, and there's not a sidecar file for zLAS like we make for LAS. We keep that information all together in the zLAS files. The writer is a simpler object. There's not as much to be done with it there. It really works at the file level granularity. It's input file, output file to convert back and forth between LAS and zLAS. And both the reader and writer objects are multi-threaded, and you can control the amount of CPU resources you want allocated to either doing the compression or the decompression. And this is true multi-threaded application coding here. It's not, I've heard there's some other term like multi-core processing or something where some applications know how to like spawn some other processes and do multiple things at one time, but they're actually separate independent processes that are running, and those can clash with each other and create I/O bottlenecks and things like that when you have like 3 different compression processes running at the same time, reading from 3 different LAS files to create a compressed format or something, is you got a lot of I/O going on there simultaneously. And we don't have that kind of issue with the way that we've done the multi-threaded support here with our objects. Error handling and reporting, important. aspect to it. All the methods that we have do have return success and failure codes. There are descriptive error strings. They're done in English. So if you're going to be working on something that's a non-English application, you'll have to kind of translate the error codes on your own to report the information in some readable format. And we do have a validator for zLAS files, just in case there was something that may have happened on the storage or in transmitting the data across the wire where the files got corrupted somehow. We can determine that there's a problem using the validator. And also, if you're in the middle of some process that may take some time, like if you're decompressing a large file or vice versa, you know, a large amount of data can take a while for an individual call. You want to have some kind of progress report, or you want to be able to cancel that operation in the middle. We do have a mechanism to support that through callbacks. And so you can find out like how far into the process you are, and you can report that information to the user, and it also supports canceling it in the middle. Spatial reference, this is a kind of interesting and tricky part with LAS. Actually, we see like many LAS files do not have proper spatial reference information in them. It's a weakness in the spec to some degree, particularly up until 1.4, because they use GeoTIFF format records to store the spatial reference information in the LAS file. So that does get kind of tricky. That did get upgraded, and it's easier with 1.4 files using well-known text format for spatial reference, WKT. But in either regard, we don't like decode the spatial reference information for you. That's something that you'll have to handle. We give you the information in memory buffers, and then you're responsible for interpreting that information. We could, we had an option of maybe like linking to some ArcGIS libraries that could do, in the interpretation of the spatial reference information, but then we'd have dependencies on other libraries that have licensing restrictions and whatnot, and we didn't want to do that. That would be bringing in too many dependencies and licensing issues, so we avoided that when it came to spatial reference. ExtraBytes, this is something that we don't see it used very commonly, but in the future it could become more common. And basically it's for the sake of extensibility, where extra information, application-specific information can be added per point within the files, and we do have support for that. But they're kind of like user-defined information. The LAS spec really doesn't have specificity regarding what might get placed inside of ExtraBytes. So again, similar to spatial reference, we don't like decode the ExtraBytes. That's going to be up to you if you're using that to handle that. But we'll give you access via memory buffers to access that information. To use the zLASlib in a project, it's really pretty simple. You just need to reference a .h file. That .h file contains all methods and properties, and basically every method, and there's documentation provided for every method in the h file itself if you were to take a look at that. And then you need to make sure the DLL, the binaries, are in the same folder as the exe that you're building in order to be able to compile and link and be able to access and use that library. So let me break out and show you some of this stuff. First off, we'll go and take a look at the zLASlib folder. Like if you were to access this, To download it, what you'd get the include folder that has the .h file and 32-bit and 64-bit binaries. README with just some extra information for it to read in a sample CPP file. And the licensing is very open. It's a Apache 2 license. So there's no problem in the use of this library in your applications. And in this project here that I have in Visual Studio, I've got the H file open. And yeah, here we go. So we see the license statement at the top of it, and then we defined our structs and enums in here, and then also things like point info records if you're going to use our structs for decoding the point record information. We'll go down and look more in this. Here's the definition for the filter where you can set the AOI that you're interested in, the returns, what class codes, what flags you want. You can also remove them from the query. You can find out if there was a query that's already set what those values were. Our point enumerator object, getting next point, next point, next point, and in different ways of accessing that information. And our reader object, here you knit it with a file name, and then we have methods that are in many ways kind of self-explanatory. Get last header, gets you the last file header in a struct that you can read or in a memory buffer. And remember, this is reading a zLAS file, but we're presenting the information in the code as LAS for the most part. So that's why there's a lot of reference to LAS, because it's just like an Esri compressed format of a LAS file. And so we can make it look like a LAS very easily. And lots of different methods associated with the reader for getting information from the zLAS file. Querying points in lots of different ways and validating and stuff like that. And then here we have the writer object definition and the convert to LAS function and convert to zLAS function for doing that reading and writing back and forth between LAS and zLAS. And then here's CPP code that I have here in a sample that I've created. I'll kind of walk through this code a little bit with you. I'm not really a C++ programmer. I do know programming, but mostly historically I've kind of worked in higher level kind of scripting languages, VB, and more recently in C#. But I dabble some in C++, and I've done that with this here. So if any of you are like hardcore C++ programmers, there may be some questionable things I've done in my code. So you could maybe give me some tips afterwards if you see something that looks funny. But forgive me for that if something looks a little odd to you. But I think for the most part, the point is just to have this code so you understand how to use the library. And so first off, let's see, if we come here, I've got a method for creating the writer object, and then a couple of methods that I use to do the conversion back and forth between zLAS and LAS. And then I have another method to create the reader object. And then with that reader object, I then have a number of other methods for, say, validating the zLAS file and getting the header and reading through the points in different ways. And then I also have an example where I, instead of using that writer object, which can decompress zLAS to LAS, I use this to convert zLAS to LAS using memory buffers. So I say, give me the header for the LAS file from the zLAS, and then I just write that memory buffer out to the file, and I get all the point records and as memory buffers of the LAS format point records, and I just write them straight out to the file and append it on there. And in the end, I have a valid LAS file because everything was done in LAS format memory buffers. So it kind of just proves that point. And then there's also a feedback class here, and this is used for the progress reporting and also the ability to catch an event from the user when they want to cancel the process. And so I've got code there to say how to implement that feedback class. And so what I do in my main routine here is I call that CreateWriter method, and then I call those couple other routines where I'm doing the conversion back and forth. And let's take a look at that code first before I run it. And we see that when I create the writer, it's just create object here and say the kind of object I want to create is the writer. And if it fails, it returns a failure code. Otherwise, it returns the writer object. And then that thing gets passed subsequently into this routine here that I have, convert zLAS to LAS. And it's just a file name for input and a file name for output. Create my feedback object for the progress reporting and cancel support, and then call the writer object with the conversion method to do the work. And similarly, with going the other direction, similar kinds of thing. But a little twist here is when we're doing the conversion and compression from LAS to zLAS, we do want a little hint on we do want point spacing as a property, like what's the nominal point spacing of the data. That's not something that's a property in a LAS file. You actually have to examine the data to figure out what the nominal pulse spacing is. And so there's a few different methods for figuring that out, some more expensive than others. And you just have an option of saying how you want to actually do that. If you scan through the file, through all the points, that's going to be the most accurate method for you. And then the conversion method there for that. So let's just start off, and I'll run through that first bit of code there. And this is just reporting. It's like, I converted a zLAS file to a LAS file, and then and back the other direction, and it was done. And it's just waiting for me to hit a key press to go through that, and it's finished. And so that's a pretty simple thing. When we get into reading zLAS files, there's a lot more methods, and it's more involved here. And I've also included code for that. In this section, similarly to the other where I create the writer, I have a method for creating the reader object, and then I go through, validating, getting the header, getting statistics, querying point records, and then I talked about doing that conversion just using memory buffers. And taking a look at this code, see we've got the CreateWriter method similarly to, I'm sorry. I need to get down a little farther to where I create the reader object. And it's just like the way I create the writer. It's just I give a different value to the object factory, telling it what to make. And then I need to call an init function to tell the reader what file to open and read from. And you can indicate how much CPU power to allocate to that. If you have multiple cores, the default, that we would just use everything. But in certain environments, you don't necessarily want to use 100% of CPU power. If something's running on a server there might be a lot of other applications running. You don't necessarily want this thing to consume everything it can possibly get its hands on. So we can throttle that CPU usage back. The validate method, it's a very simple thing, just on the reader, can validate a given file. And if there's a problem with it, the reader will have like an error string that you can get, or an error code, to point at something that might be specifically that we can identify that seems wrong with the file. Something's wrong in the header, something's wrong with a certain point record. And then getting access to the header file, we load the header information into this struct, and then I just go in my code and I just print out all the different properties that are stored in the last header that's been pulled out of the zLAS file, and echo that and report that out to the console window. And I've got some tests here, like if the version of LAS is less than 1.4, then I know that the way the number of points potentially is different. There's a different upper limit when we get to LAS 1.4, and the number of returns can be different. Older versions of LAS support just up to 5 returns, but newer versions of LAS go up to 15, and so there's some conditional code there depending on what format of LAS was used to make the zLAS file. And then getting at the statistics information that we've stored, like we know whether the point order has been sorted into those spatially coherent, sets of points where if they're near to each other in XY, they're close to each other in the files. We know whether that had been done or not when the zLAS file was made. We have a record of what the original decompressed size of the LAS file was. So if you were to go through and decompress a bunch of zLAS files, you know how much disk space you're going to need to store the decompressed LAS files. That's something else that we can get at. The coordinate system info that's read into a memory buffer for you to interpret. And but we will tell you whether it's using the more older style variable length record format for the spatial reference information, or the newer WKT format for the spatial reference information. So you're going to use a different way of interpreting the spatial reference information based on what format was used, and that's based on what version of LAS, generally speaking. Although the committee did try to build into some flexibility, like in the new LAS 1.4 format, you could kind of use either one depending on your preference, although the WKT is what's recommended. Getting at class code information, it's a simple call to the reader to get unique class codes. So as I said before, the last header, the format doesn't store that information for you. To have to scan through the whole file to find out what class codes are present. But the zLAS files know this, and we store it and can return it without having to scan through everything. And then my code just spits that out. What are the unique class codes that are present? Similar for returns, getting how many return 3s are there? How many first returns are there? That kind of stuff. We have that information we can report out to you. And my code is just going and reporting that information. And then also per point, or let's say summarizing the points, like what's the Z range of the data? What's the range of intensity? What's the standard deviation of the intensity values that's useful for creating like stretch renderers, for example, to have that information. So we have like min, max, mean, standard deviation for a bunch of different attributes that are stored in the LAS files, and you can get at that very easily. And querying points, there's different ways you could go about querying for points. You could just say, I want to look through all the points from the zLAS file, and I'm going to do something with them analytic. or whatnot, or you may have an area of interest, or you may say from record number n to n plus 1,000 or something, give me those points, and we support those. And along with this point data mask that I referred to before, where you can indicate which attributes you're interested in, so you don't have to decode or decompress all attributes, saving some computing resources if you're just going to focus on something. So I have a few different ways in my code that I'm just giving different examples about how to query points from the files. And then reporting some point record information like the first endpoints in the file. Here I'm getting just based on a number of points with a starting point ID, so I can go from point N, read the first 100 points or something, and then report that information out. Here I set up a spatial query and then use a point enumerator. So I create a filter object using this create object method and say, I'll tell it I'm making a filter. And then with that filter, I set an AOI with the XY extent that I'm interested in. And then in this case, I say I also want points not just within that rectangle, but just the class code 2 points within that rectangle. And that's the filter setting. Then I go tell the reader to get the points within that honor the filter setting. And this will return back a point enumerator for me. And I can go through and I can set up, like in this case, I just set up some 5K arrays. So I can read, in this case, 5,000 points at a time, reading it in chunks for the sake of efficiency. And then I loop through chunks of 5,000 points at a time until I hit the end when there's no more points left. And then I just know to quit because then I'm done. And then the last method that I have written here is converting to LAS using the reader. This isn't something that I would recommend for real use. We have the writer object that'll decompress zLAS to LAS, but this is just a proof of concept saying we get those memory buffers from zLAS in LAS format, and I just turn around, write them out to a file, and lo and behold, it's a valid LAS file. And so this code is just going through that process of getting those chunks of memory buffers and writing them out to a file. So let's just run through that code. And here's the first thing, the step through getting the header information from the zLAS file and echoing that back out to the screen, what version of LAS file it is, what the creation software was, TerraScan in this case. Just if you're familiar with LAS, standard header information here. And then the code that's looping through, what are the unique class codes that are present? What are the unique returns that are present and the point counts associated with them? Also a little extra information about last of many returns and that kind of stuff there. And then I also talked about looking at the stats for attributes like intensity and scan angle, the min, max, mean, standard deviation. And then through the queries that I made for the point records, just spitting that information back out. In this last example, I was only interested in the X, Y, Z geometry, so that's all that's echoed here, whereas some of the early ones had the point ID number, return, class code, intensity value that I included there. And then I just also stepped through here where it did that conversion to LAS using memory buffers. And so if I go after that, the file that was made, I think I have a folder open for that. So here's an output folder where I was writing things to. And I use the reader object to create this LAS file. And so if I make a LAS data set from it, let's take a look at it. And output. And it was the reader that gave me the memory buffers that I used to create this LAS file with. And we can go take a look at it. The header information is here. I can go calculate stats for it. And so we scan through the file to get extra information reported for us. And I can drop that LAS data set into my map and view that. So let me go back to our slides kind of to wrap things up in a sense. And then I'll open things up to questions if you guys have some. Availability on GitHub. I've listed the path here. You go to this location, you can find the IO library, download it. It's a very easygoing license. No problem using that. And this specific code that I have running through that demo, I'm happy to share it with you. If you would just send me an email, and I'd be happy to send it right off back to you. So with that, I'd like to open it up to any questions that you might have. Anyone? Here you go.
If you use this library, do I need to register or just download it?
You can just download it. You don't need to register. It's just you go to the path that I had listed, and you can just download it straight. You're not going to be asked for any information. Okay, don't be shy. Any questions? We got a few minutes. You good?
Have there been efforts to bring this type of LAS data access into cloud services? I know this is a very low-level library, and one of the problems that I've been having is taking the desktop applications I've written and scaling them, because inevitably the code that I've written doesn't want to run nicely when I need 20, 30, 50 threads all accessing the same data set in the cloud.
Mm-hmm. Well, this specific kind of functionality, no, I'm not familiar with that. It could be, there are different ways of having the data on the cloud and accessing that information, and I guess it depends a lot on what it is that your app is doing. Within the last year, Esri has come out with what we call a point cloud scene layer, and through our indexed 3D scene layer format, I3S, we're storing large point clouds on servers and serving that information up very efficiently to clients for rendering in 3D, for example. And that's how we're very efficiently sharing large point clouds to clients. Now that's for certain kinds of applications, right? So it's not the LAS format, and it's not really specifically zLAS. It's the I3S format, but that's designed really for efficiently serving a large number of clients, over the web, data through use of levels of detail and tricks like that to speed up and make things efficient. But I don't know, is that related really at all? It's maybe a sidestep or a tangent to your question. All right, well, thank you, and have a good rest of the conference.